Good morning, friends. I'm Dr. Tyagarajan Satish Kumar, working as faculty in the Department of Biotechnology, Marguru College of Technology, Coimbatore, Tamil Nadu. So today I'm going to give an overview about the algorithm of BLAST, how it can be executed by using NCBI. You know, BLAST is a very potent heuristic-based algorithm which can search against the protein sequences distributed across a very potent database. So today we can see how we can retrieve a sequence, a protein sequence from NCBI, how we can blast it, and ultimately we will also discuss about the usefulness of the blast, and even we will comment about or we will interpret the results what today we are going to generate. So first you have to go to NCBI websites. So type NCBI. So automatically you will get a Google page like this. You create a new tab, and then you see the NCBI page will appear like this. This is a periodical. There will be periodical updation in NCBI. So very carefully we have to watch. We have to see the page oftenly. Now you can see there is a pull down menu like this. Defaultly it will all database will appear. So you click this pull down menu, and first here we have to retrieve the protein sequence. Now you click the protein. So if you want to retrieve a nucleotide sequence, you can select this nucleotide, or otherwise you can select the protein. So today we will take the very hotspot protein sequence, that is human coronavirus spike protein. You can type COV spike protein. So now you can see a list of spike protein variants which has been deposited in NCBI database will be projected. So for today's experiment, we can select any one spike protein. So we will select the first spike protein, which is having the accession number ARU07610. So now here you can see different options, whether you want to look at the domain portions of your spike protein or you want to retrieve only the FASTA sequence. So today we want to retrieve only the FASTA sequence. So just click the FASTA which is present here. So now if you want to open the sequences in a new page, you can create a new tab and you can retrieve. So now the sequence is ready. Anyone must be familiarized with the single letter amino acid code, which is very, very important. So now very successfully we have retrieved the spike protein of human coronavirus. So now we have to blast it, right? So here, if you want, you can open new page. For learners, you can go for a new page. Again, you type NCBI. NCBI BLAST is very, very famous. Many different universities are hosting BLAST search engine, but still NCBI BLAST is very, very famous. So type NCBI. Even you can see BLAST over here, but again for learners, it is better to enter into NCBI. Now, right top corner, so here you can see BLAST. Now BLAST tool is available, so you can click BLAST. So now variety of BLAST tools will be listed by NCBI. So this is a BLAST which specifically search nucleotide sequences. Right, you can see protein blast, which very specifically search protein sequences. In the middle, you can see a translated blast, right? So if you give a nucleotide will be translated into a protein, and that translated protein will search against a protein database. So that is BLASTX. So now here you can see a protein is there, C blastian, which will search against the translated. So these two things are will not be covered under this session. So we'll go for a protein blast. Since we have retrieved protein sequences, the apt blast is protein blast. So now click this. So you select this protein blast. So the given sequence is a protein. It will search against only a protein database. So that's what protein blast means. Now the protein blast page will look like this. Here you can see how to paste the protein sequence. So now hereafter we will call this protein sequence as a query protein sequence. Now already we have selected this query protein sequence here. Select along with FASTA format. So what is a FASTA format? FASTA format is a format which starts with a greater than symbol. So now here you can see a greater than symbol. So you have to entirely select and copy the protein sequence. Then you can paste over here. Without FASTA sequence or any other supported sequence, the BLAST tool will not function. So you have to paste the protein sequence only in FASTA formats. Right? Now you can give a job title. Just you left click, you will get the heading of the protein sequence that you can give as a job title. Now we have to optimize one by one. First, you can go for a database. When you click the pull down menu, it will give many options, many different databases. So according to your work, you have to select the right database. But today we are going to we are doing a very generalized blast. So instead of selecting a very specific database, we will select the default database, that is non-redundant protein sequence database. Shortly, it will be termed as NR. For any generalized search, please use this NR. If you are having any very specific reference-oriented proteins, then you can go for a reference proteins. Or if you feel that very particular protein sequences are deposited in UniProt or SwissProt database, you can select SwissProt. Or you want to blast the query sequence across some patented sequences, then you select this patented. If your intention is very general, or you have not formulated any very specific strategies, then please select this non-redundant database, right, which is termed as non-redundant protein sequence database. Defaultly it will present like this. And this is optional. For today we are going to exclude these things. We are not going to search against any organism oriented protein sequences, right? Now we'll go for this. You can see multiple blast app has been listed over here. This is position specific iterated blast. Again and again and again you can iterate, and finally you can converge the protein sequences, right? So we are not going to look this position specific iterated blast or pattern fit iterated blast. Instead, we'll select a very specific fast delta blast. So full form for delta, you can see it is listed over here. Domain enhanced lookup time accelerated blast. So you can select this delta blast, right? And always most of the people will immediately blast over here. So we should not blast at this juncture. You select this option so that the results will appear in new window. We have to optimize the algorithm. So now click this algorithmic parameters. Now you see the purpose of optimizing various algorithmic parameters will reduce the running time. So that is the great advantage of BLAST. Now first here we'll go for a maximum target sequence. Select this. You can see umpty number of, that means if you select 10, only top 10 alignments will be projected in the results. You select 500 top 50 alignments will be projected. So now we are going for a generalized blast. Instead of selecting 500 or 1000 or 250, we can cut short the number of alignments to 50. So first you blast, take 50, see whether your outcome is satisfied. If not, again blast it with more number of sequences. You select 500 or 1000, then running time will be increased. Computationally, it will be intensive. So always we can cut short this 500 to 50 sequence. Ask the tool to project only top 50 sequences. Now, before entering into this threshold value, we'll go for a word size. Here you can see delta blast is projecting only two different word size. So what is a word size? How many number of characters in the query sequence will be matched against the database sequence? So that is the word size. So if you select three characters in the query sequence will be matched against the three characters in the database sequence. So in BLAST algorithm, there is an important step termed as preparation of word list. So if you go for a 3, the query sequence will be split into 3 characters, overlapping 3 characters. If you select 2, then the query sequence will be fragmented into 2 characters, that is overlapping characters. Now there is only two options. Either you can select 2 as a word list or you can select 3. So selection of this word size is purely based upon the number of characters present in your query sequence. You can see approximately 1500 plus characters are distributed in the query sequence. So in order to reduce the running time, it is wise to select the word size 3. So selection of word size is directly proportional to the number of characters distributed in the query sequence. If there are more characters, you select a word size of 3. If there are less characters, then you select a word size of 2. There is no much more options, right? So today we will select word size 3. Now we go for the selection of matrix. So default matrix is Blossom 62. For any learner, better blast with the Blossom 62 and observe the results. But for middle learners and even for advanced learners, you can try with the higher version. So what is full form for Blossom? It is a matrix which is constructed from a substitution from a database, from a protein database termed as blocks. So full form for Blossom is blocks substitution matrix. So today we will select the Blossom 80. Right? So that means this is a matrix which is constructed from a set of protein sequences whose similarity is approximately 80%. Right? Our intention is to find the similarity and hence we can select this type of matrix. Now when you select the matrix over here, automatically you can see there will be a gap opening or existence and gap extension penalties. So even though the numerical projected here is 10 and plus, you have to observe, you have to read as minus 10 and minus 1. These are all penalties. Say if you want to change the penalty, you can change, or otherwise you can leave. For example, if you select say PAM 250, you can see there is a change in open penalty and extension penalty. So whenever you select a particular matrix, the tool itself will give an optimal opening penalty and extension penalty. Here the ratio was 1:10. That is the opening extension penalty is 1, opening penalty is 10. Always the opening penalty should be greater. Then only the gaps will be placed at the right position and you get the right alignment. Right? So if you want to change, you can change, but better you can optimize an opening extension penalty from 1:10 and 1:15 for better similarity score. So today we will leave the tool's decision. Opening penalty is -10, extension penalty is -1. Now after formulating this, now we have to move over here, threshold value. So the threshold value for now you can see this is there is no pull down menu, right? It is user defined. You have to define your own threshold value. Now you have selected a word size of 3. So you observe Blossom 80 matrix. You see the diagonal that is matched. Say alanine, alanine, glycine, glycine, tyrosine, tyrosine. You observe the values. You exclude serine, tyrosine, phenylalanine, and tryptophan. These are all very resistant amino acids, and their score will be very higher. So you exclude these 4 amino acids. You observe other amino acids. You take an average value. Based upon the average value, you can construct the threshold. Say if the average value of other match, glycine, valine, leucine, if their match is the average value, say it is, say, for example, 4, for a selected vertex of 3, 4 plus 4 plus 4, you will get a 12. So a generalized opinion is you can set the expected threshold between 10 and 15, right? So now today, uh, the value we can go for 12. Assume that the average match value for each pair is 4. So today the selected vertex is 3. So 3 pairs, each pair it is 4. 3 pair, 3 into 4, 12. So I have set threshold value as 12. That means during search, if the threshold value is greater than 12 for 3 characters, those area will be considered as a hotspot. Values below plus 12 will be filtered. Value above 12 will be taken as a hotspot. Only that particular area will be considered for alignment, right? So whenever you go for a blast, you select the word size, you select the matrix, you select the gap opening extension penalty, and then you use your wisdom and you set the threshold value. Don't set threshold value at the initial level, right? Now you can see there is a low complexity regions. If you go for a nucleotide value, if you go for a nucleotide sequence, then you have to go for select this, because nucleotide may contain repetitive sequences, say AT, or multiple GC repetitions, multiple AT repetitions. So you know when the complexity number is less, when there are more repetitions, repetitive sequences are meaningless. They may contribute for introns, useless, junk portions. So during alignment, we don't want to align any junk portions or which we consider as a useless. So non-repetitive sequences play a major role. So they could act as a good exon portions. So when you select nucleotide sequences for your blast, you can think about this filtering low complexity. But for protein sequences, there is no need. You can see there is no repetitions over here. Now here you can see it is L. So now here you can see it is A, G, V, P, F, Y, L. There is no repetition of, say, for example, if you take YL, you take this MF, there is no repetition of MF, 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 MF. Or if you take this LK, there is no repetition of LK, LK, LK. So repetitions, when there is a repetitions, you can ask the tool to filter those repetitions. You feel repetitions are useless. For protein sequences, you may not get that chance. The repetitions will be very less, and hence we are not using, we are not going to exercise this particular option, right? And finally, I told that we are not going to exercise anything about PSI blast. So this is 5% level of significance, delta blast, 0.0. If you want, you can change just 1%. So it is better to start with the, we should have a humble start. We'll go for this 5% level of significance. So 5%. Now you can see, don't forget to enable this particular checkbox. There you are asking the tool to generate the results in a new window. Now everything is ready, blast it. So be humble, be maintain a kind of patience. So you have to wait for a few time, because the number of characters today what we took is 1000 and odd. So it will take some time for the blast to blast it. So for learners, what I suggest is select a very simple peptide. It could be an octapeptide or a nanopeptide, or it could be a decapeptide, or the number of characters should be very less. 20 characters, 25 characters, 10 characters. You select such kind of simple oligopeptides, simple peptides and polypeptides for blast purpose. Or even you can select say 120 characters or 150 characters, a very simple protein. Don't select 1000 and odd. So now here you can see blasting time is little bit high. because 1000 characters present in your query sequence, right? It has to match with the thousands and thousands of protein sequences distributed in your database. So it will take time. Don't refresh automatically. The page will refresh patiently. You wait. So we can see. So here a request ID will be there. You can see the time, how long it will take for every 19 seconds or 22 seconds or 25 seconds. The page will automatically refresh and finally get the result page. The result page will have different functionalities. Uh, we are interested with the 3 to 4 tabs. Defaultly, you will get the first 50 alignments. Your query sequence will align the sequence distributed in the database, and that description will be reflected the results page. Yes, now the result is ready. So here you can see what it will give the summary or a synopsis of your blast. You have used Delta Blast, you have used non-redundant database, and you can see the length of the query sequence is 1358. Now here you can see the 4 different tabs. Automatically description tab defaultly it will be reflected in the results page. Here you see this particular e value and percent identity is very important. Actually, we are expecting a very negative e value. Today we got the e value 0, but still here you can see this 100%. We should not expect in any bioinformatics oriented result. Since we retrieved a sequence from the database, we have retrieved. That is not, you have not purified a protein, you have not sequenced it. So we took a protein from a database, so and we have blasted it. So the query sequence again, it has aligned with its own duplicate sequence. So remember, 100% identity result should not be expected in any bioinformatics, right? So now here you can see 93%, 99%, 99%, 99%. Here you can see 99, 98%. So top 50 alignments you got what protein. So this is the protein in the database. This is the protein in the database. So 50 different proteins distributed in the database is aligned with your query sequence. So this is the description. And here you can go for alignment. So you click the alignment. Now here you get like this. So this is alignment, first rank alignment, and this is second rank alignment. We scroll down, third rank, so like that you will get 50 ranks. Now just we will see. I told that 100% result is useless, so we'll go for here. Now here you can see this is the query sequence. That means the sequence what you have given for blast. Subject sequence, this is the sequence which is distributed in your database. Now here you can see the match or identical characters was represented in the middle. So M means methionine, the first position, methionine is present in your query sequence. Same methionine is also present in the database sequence. So the identical characters in BLAST will be represented as letters. So the middle portion denotes the identical characters distributed or present or aligned between your query sequence and your database sequence. Right now, here you can see there are 1357 identity, and you can see positive is nothing but a similarity. There is one increase in similarity, acceptable similarity. Here we have to search, and in BLAST it will be represented as plus. So we have to search for the plus over here. Sure, there will be a plus. There will be a plus. So if it is invisible, no issues. You can increase it. Search for the plus. Yes, now here it is present. So here you can see there is a plus. So there is alanine present in your query sequence, and serine is present in your database sequence. We feel that instead of alanine, if we replace with serine, there is no big difference. You can see the side chain of alanine is methyl group, side chain of your serine is a hydroxymethylene. The difference is only one oxygen. CH3, that is alanine side chain. CH2OH, when you condense, it will become CH3O. So the difference between alanine and serine is just only one oxygen atom. So if you replace alanine with serine, we are not expecting a big change in the structure of the protein, and that way we are not expecting a big loss over function. So this we are telling as an acceptable mutation. That means the replacement of alanine with serine will not affect the structure as well as function of the protein. So we feel it is a kind of silent mutation. So that is similarity, right? So additional one here, 1357 is identity. Identity means exact match. So alanine and serine was added over here, 1358. Again, you can see 100%. And even we can see or observe, if possible, we can look for unacceptable mismatch. That means it will not be accounted for similarity. So that will be represented as this gap. It will be as a space, small space will be present. So here it is not. We'll scroll down. So we'll try to observe any unacceptable mismatch. Now here you can see the third rank. You can see an unacceptable mismatch. So now here you can see L and F. So now here you can see it was not indicated by any symbol. So L is leucine, F is phenylalanine. Leucine is hydrophilic in nature, phenylalanine is hydrophobic in nature. Leucine is aromatic, aliphatic branch, whereas phenylalanine is aromatic. No way the molecular weight or polarity doesn't match. So now this is unacceptable. So if you replace leucine with phenylalanine, the structure will be collapsed, the three-dimensional structure will be collapsed, the function will be collapsed. So this kind of replacement is actually termed as unacceptable mutation. It will not be accounted for similarity or your positives. So in the top, we look for a positive, a plus symbol is there. So when there is a plus symbol in the mismatch, that shows that it is an acceptable mutation, it will be accounted for positive. Whereas when there is a mismatch, and if there is no symbolic representation, that shows that it is an unacceptable mismatch. And finally, here it is very hard to find a gap because almost you can see 99 or 98% similarity is there. Gap will be indicated by a hyphen mark, and it will be present over here. So here it will be present over here. So now you can look, you can see this alignment. Now next, I'm skipping multiple sequence alignment. I'll go for straight away. I'll go for phylogenetic construction. We go for a description tab, right? And here you can see two options: multiple sequence and distance tree. For this, you have to select certain sequences. Now default here, all 50 sequences were selected. We don't want all 50, so we will select the sequences. Now select sequence 1, 100%. You select randomly 99.56. You select randomly here 99.51. You select randomly say 99.04, 99, 98.9, 98.97. Here you can see 6 sequences we have selected. So check out this box, you unselect, and then here on the left side you select the sequences with the different identity percentage. Then we go for this. For the selected sequences, now you construct the phylogenetic tree. So you select, you select this distance tree, right? So now automatically you you can see a fine and a fantastic phylogenetic tree, right? So if you feel that this particular layout is not good, this particular layout is not convenient for interpretation, right click, right, right click, you can see layout, and better this is rectangle, you can go for a slanted cladogram. So now you will get the slanted cladogram, right? Now here you can see this is the query sequence. Yellow color indicates the sequence what you have given. You can see it is sharing the very high similarity of this particular protein, right? Or still for more better clarity, you can go for what to say. Try with again radial, right? This is an unrooted. The other two is rooted. Now this is unrooted. So better we can go for slanted. So different topology is there for representing your molecular phylogenetic tree. So this is unrooted. Rectangle will predict a rooted. It will predict the root. Similarly, slanted will also predict the root. So here you can see the root. Yes, now here you can see. So now this is root. Right now here you can see these are all ancestral nodes. These are all leaves, phylogeny. So you can come to a conclusion that your query sequence is sharing more similarity with this particular sequence, and a good similarity is shared between these two, because you can see all four different sequences are coming under one ancestral. And even for better clarification, instead of fast minimal evolution, you can go for neighbor joining method. Right now again, retree will be drawn, it will be predicted. You can see it is rectangle. Again, right click for a slanted cladogram. Here you can see a tree is a little bit differently predicted. Again, you can see your query sequence is sharing uh, more sequence similarity with this particular sequence. And this is termed as an ancestral node. This is another ancestral node. These are all branches. This is the root. So these are all some of the parts of a phylogenetic tree. So now for final analysis, for further docking or other thing, you can consider, you can construct this phylogenetic tree, you can observe something, you draw some conclusion about the evolutionary tree. Say for docking purpose, you can take this particular protein, you dock this ligand. Again, you take another this protein, because this protein is also sharing the same similarity with your query sequence. So you take this sequence, you dock with the same ligands, you compare the protein ligand docking results. And finally, you can go for a combinatorial chemistry to synthesis of ligand. So friends, hope I have skipped multiple sequence alignment due to lack of time. So before entering into, I have given just an overview. This is not sufficient. This particular video is targeted for only basic, very basic learners. For middle level and advanced learners, you should be very familiar with the algorithm of the BLAST. Then only you can do more iterations. You can touch a position specific iterated BLAST. You can construct a phylogenetic result tree, and then you can find the apt similarity oriented sequences, and then you can go for protein ligand. Thank you for patient listening. Thank you. Thanks a lot.